So continuing in our journey of the determination of the bending moments of reinforced concrete beams, here is very simple. Now that we know the forces that act in the section, we know that for equilibrium, the capital C, the force in concrete, has to be equal to T, the forces in the reinforcements. The forces in concrete, as we saw previously, it's equals to the volume of the stress block times its stress. So it's going to be, as we said, alpha 1 times F prime C, okay, multiplied by its depth, C, multiplied by the width of the compressive stress, which is the width of the beam, okay? So this was very simple. And as we saw, the forces in the reinforcements are equals to the cross-section area of reinforcements times the stress in the reinforcements. The stress in the reinforcement, we usually use the yielding strength. The yielding strength is what we classify it as the limit that we usually use for design, because after yielding, you would have immense deformation. So the yielding is actually the limit that we use. All right. So the position of the neutral line, whenever we know the section, so if the section is known, that means we know its width, we know its height, we know the cross-sectional area and the reinforcements. We can determine the position of the neutral line. And Yuri, why is this important to determine the position of the neutral line? It's important because whenever we want to calculate the moment, the bending moment, we have to have the lever arm, and we cannot determine the lever arm without the position of the neutral line. Ah, okay, got it. So this is what we're doing. So the position of the neutral line well, you just have to separate this equation and isolate A. Okay, so it's AS times Fy. Okay, so the area of reinforcements times the yielding strength, and divided by the Whiting stress block. Alpha 1 times F prime C times B. Okay. You also can use, so far, remember that beta 1 and alpha 1, they are already 0.85. So if you want, you can already substitute this. So the equation would be like this. This is what actually the equation that we usually show in textbooks. Okay, this is how we determined. And the bending moment is the same thing. We now know how to calculate the lever arm, which is, as we said before, d minus a over 2. Okay, and the force of the section, we can just use either the compressive force of the concrete or the tension of the reinforcement. Tension of the reinforcement is easier because we have smaller parameters to determine. And this is pretty much the equation to determine the bending moment. And here we are calling nominal bending moment, okay, of the section. Okay, whenever you have a non-section. Okay, so this is quite funny. Something that is also need to be addressed is the effect of stress and strain. Whenever we are designing reinforced concrete beams, we need to assess if the amount of steel that is within the section is going to yield under the nominal forces. And why do you want that, Yuri? Why do we need this? We need this to guarantee, we need to guarantee that we have the ductility being satisfied. Okay, we have to have the ductility in the beam by using this relation. So whenever we have the bending imposition of a beam, we want the beam to deform, all right? Whenever a beam is deforming a lot, we know that the steel is yielding. So that gives plenty of time if we're going to have a collapse. So this is important. Whenever your section is not controlled by tension, in other words, it's not ductile, the bending moments actually we tend to use a penalty. We're going to address this later on, but we usually multiply by a factor, and this factor considers if your section is tension control, ductile, or compressive control, which is not as ductile. And then whenever your section is not ductile, we tend to penalize the bending moment more. Okay, we're going to address this really soon. So just to conclude this, the checking if the yield, the steel yields is quite simple. We have the strain relations here. We know it follows a linear behavior because it's based on the theory. We know that we have the ultimate compressive strain of concrete, and here we want to determine the strain of steel. We can do here the simulation of triangles. It's quite simple. Now this guy is for the depth of the neutral line, and this guy is going to be for this part here, which is the depth d minus c. All right. So putting this into an equation, ultimate strain of concrete is equals to c, and here we have the strain in steel. It's equals to d minus c. Right, if we isolate the strain in steel, we have this equation here. Okay, so whenever we have the position of the neutral line, we have the depth of the section until the reinforcements, and we know the type of concrete, usually 0.0035. We can determine if this guy is going to be bigger than the strain in the reinforcements. Also, it's important to highlight that the yielding strain in the reinforcement is equals to the it's actually the opposite here. Hold on. We know that stress equals to modulus of elasticity times strain. Okay, so the strain is going to be the modulus of elasticity divided by Fy. Okay, I think for steel I think it's 50,000 KSI, if I'm not mistaken. And this guide depends on the type of steel. If you have 60 KSI steels, divided by 60. Okay, I think I used this wrong. It's actually the opposite. Yeah, because it would be too low. Fy on top, and here is modulus of elasticity. Okay, it's 50,009, 59,000, and here is 60. Around, okay? It depends on. So you guys can have an idea. For example, if we divide 60 by 59,000, 0.101, something like this. I think it's actually 29,000. Here's 29. Yeah, got it. Sorry guys, because usually I don't use KSI units. Now let's see. I think that's about it. 60 divided by 29,000. Exactly. So around 2/1,000. Okay, so usually it's around 2/1,000. Okay. For the last part of this class, we're going to do the example number 1, which is a very interesting example. I'll talk about this in the next video. But the idea here is how much uniform loading can a 14 feet span simply supported reinforced concrete beam support if we have this cross section here. Okay, if we have a 20 by 12 inches section with 4 number 8 bars, like how much would that beam support? Okay, so stay tuned for the next video.